Hello everyone. So, am I audible? Can someone just write in the comment, am I audible or not? Or the screen is visible or not?
Yes.
Yes,
Okay,
sir.
okay, fine. Okay, so today is the first. So, hello everyone. So, today is the first lecture, first tutorial kind of. So, initially, I will just discuss some introductory theory, then we'll discuss about some problems. Okay, is it okay?
Yes, sir.
Okay, fine. So, first, let's check what we are in this course. We'll study about the light matter interaction, right? So, what is the difference between matter and light? Just roughly. So, we have suppose we have electromagnetic wave, that is light, and another light matter interaction, right? And another we have matter. So, what is the difference? Like main difference between these kind of in terms of energy states or level, we can say. So, in lights, what we have energy levels, right? Also, but all are, suppose this is your state 0, 1, 2. If it is a harmonic oscillator, then all the gaps are uniform, right? All are h cut omega, some kind of. But in matter, what you have, this is not a uniform spectrum. So in matter, if you draw similar thing, so one is like this, another is like this, like this. So this is your E1, E2, E3. So energy spectrums are not uniform. Okay, and in this course, what we are going to study, we are going to study the light matter interaction. So this light will interact with this matter. So this uniform spectrum of energy will interact with this non-uniform. But what we can do, we can simplify this, right? So what we simplify, we assume the matter as a two-level state. So actually matter has many energy states, right? E1, E2, E3, like infinity number of states may be there. But we simplify the matter as a two-level system. And how we can do that? So initially your matter, whatever matter you have, it has highly non-uniform spectra of energy, right? And it is interacting with this light. Suppose I assume my light is a highly monochromatic light, highly monochromatic. That's why we have written a single frequency omega. So this light is made up of quanta of energy called photon, and each quanta is h cut omega, right? So this light is made of h cut omega is what? One quanta. That means one photon energy. So omega is just a single number. So it is assuming it is highly monochromatic. So this is interacting with this matter, which is highly non-uniform spectrum, right? So now tell me how we can, why we can simplify this as a two-level state, because actually matter has many energy level, right? So why we can assume that is a two-level state? Yeah, gaps are different, that I understand. But when you study light matter interaction, like in the first two lectures you study, right? You assume one is ground, one is excited. Why two? What the other energy states like E3, E4? There may be E4, right? Why they
Yeah,
are
so
not?
yes,
Yes, tell.
suppose we have a laser light, right?
Yes.
It's a monochromatic light,
Hmm.
and if its light is coming, and how can we sure that the light itself it is in ground state? Because you represented 0, 1, 2, etc. as a light energy levels, but in real, like a laser light, how can we represent light as a zero state, 1 state, or 2 state? Did you
Light
get my
as
Did you get my point?
I didn't get your point clearly. Can you once
Sup-
repeat?
Suppose a laser light, right?
Yes.
Laser light itself is a monochromatic light.
Hmm.
But when the light is coming and interact with the matter, how
Hmm.
can we show light itself a ground state or uh, first, because you represented 0, 1, 2, etc. as a energy level of light.
I'm just representing like harmonic. Suppose your light is monochromatic. So what will be the energy? H cut omega, right? That's what I'm
Yes.
just giving an example.
But what is the meaning of ground state, 1 state and 2 state? Ground state means itself a equilibrium state, right? But photon has a excited state or ground state. That is my point.
So you can assume that what your electromagnetic wave is like behaving like a harmonic oscillator, right? Hello.
Yeah, yeah. Tell.
So this is not exactly light, I can say, but I'm just telling. Suppose you can assume like a harmonic oscillator model kind of thing. That's why.
Okay. Please carry on.
Hmm. So your light is interacting with matter, right? So now, so suppose we have many energy levels E1, E2, E3, E4. Now, if we want to write the Hamiltonian of this matter, how it will look? suppose I want to write the Hamiltonian H of this system, of this matter only. So it will look like how? Suppose it has many energy levels, like suppose this is 1, 2, 3, 4, whatever, or in general n. Then it will look like, suppose how? 1 has eigenvalue E1, right? So it is En n comma n, summation over n. So this will be your Hamiltonian of this matter. Now your incoming light, it has a frequency, you are assuming monochromatic, so each photon has energy h cut omega, right? So unless if the gap is h cut omega, others it cannot interact with the light, right? Only those energy levels that has energy gap h cut omega will interact with the incoming light that has frequency omega, right? So even though you have many levels here, but as your incoming light wave you are assuming as a monochromatic, so it has single frequency omega. That's why you can approximate it as a like this. So only suppose E1 is your, this gap is h cut omega, E1 and E2. So only these two will survive. I mean survive means take part in the interaction. E2 2 comma 2. So this you can approximate. So this is your two level approximation. So this is E2 minus E1 has to be almost equals to h cut omega. Then only you can approximate your matter of many energy levels of non-uniform energy gap as a two level atom or two level matter. Fine. And another thing I want to discuss is that will be useful later, that is the parity operator. Okay. Before parity, just finish this part. Okay, I will come back to parity operator later. Okay, just initial 5 minutes. Suppose just you have a single hydrogen atom. Okay, just little bit of atomic physics. So hydrogen atom, what you have? You have a proton here, and you have an electron here, and relative separation is suppose R, and electron has a spin S, and this nuclear has a spin I. Suppose in this case I equals to half only and S equals to half only. So I mean the simplest approximation under Bohr approximation, suppose what will be the Hamiltonian of this system? So Hamiltonian has how many terms? Suppose one is p square by, first is the kinetic term, p square by 2 mu, right? Mu is the reduced mass. If this is mi and if this is me, so this is mi me by mi plus me. This is the reduced mass and the electrostatic interaction. In general, if this is for hydrogen, z equals to 1, but in general you can write z square by 4 pi epsilon 0 into the relative distance, here r. So this is your Hamiltonian under Bohr approximation, right? So under Bohr approximation, like you can draw this. So this is Bohr only. So you have n equals to 1, n equals to 2, n equals to 3, right? So under this approximation, what are the eigenvalues of this H? You know that from Bohr. I'm not deriving anything, just go through the things. So you can just show that eigenvalues of H is given by En equals to some minus 13.6 by n square electron volt. Like, right, that we know. So you have n equals to 1 level, 2 level, 3 level, and all the levels are degenerate. Degenerate in the sense all have same energy, 13.6 by n square, right? Fine. And in this case you can, what is the state you can write? State n you can write as like n, then L runs from 0 to n minus 1, then ml, ms and mi. These are just atomic physics, right? L runs from 0 to n minus 1 and ml runs from minus L to plus L. So under Bohr approximation, this is your picture, right? And energy E only depends on n quantum number. It doesn't depends on L or ml or whatever. That's why all the levels, suppose n equals to 2, here L equals to 0 and 1, but both have same energy as given by 13.6 by n square. Suppose n equals to 3, L equals to 0, 1, 2, but L equals to 0, 1, 2, all levels have same energy, minus 13.6 by n square. That's why we call these degenerate levels, okay? Now this is your simplest approximation. Now after Bohr, what we do? Next, in atomic physics, what it comes? Next approximation is like you introduce the multi-electron, like many electrons are there, suppose. then what will happen? Wait a minute. Is my screen visible? Hello, is my screen visible now? Don't see anything. Okay, okay. Okay, so there is only one electron in hydrogen. Now we go to multi-electron. In multi-electron, what you have? You have potential energy Vr. It doesn't look like 1 by R now. In this case, Vr was what? 1 by 4 pi epsilon 0 Z square by R. So 1 by R dependency was there. Now that dependency is removed because now we have many electrons. This is your nucleus. So this is your outermost electron. But here also you have many electrons. So potential energy now it will look like there will be some effective charge. This is called effective charge and 4 pi epsilon 0 R. So main thing is it will not be 1 by R proportional to. Okay, and that will lift one degeneracy, and because of that you will have now eigen values of H will depends on N as well as L. Okay, so you go to multi-level system now. So E now depends on N and L. So N equals to 1, it has L equals to 0 value only, right? So this energy level will remain same. But N equals to 2, it has L equals to 0 and 1. So it will break into two parts. One is L equals to 0, another is L equals to 1. Similarly, this will break into three parts. One is L equals to 0, 1 and 2. So this is you called one s orbital. S means L equals to 0. This is 2s. So in Bohr picture, it was only En. Now in multi-electron, now after Bohr, you go to multi-electron. So Bohr was the first person. Next, it was multi-electron. Okay, then En comma L. You will remove all the degeneracy one by one. So this is 2s and 2p. Next here you have n equals to 3, and the spectroscopic notation, you in this case you write like this: n and l. Okay, n and l. So first term transfer n value, second one is l value. So 1s, 2s, 2p, then 3s, 3p, 3d, like this. Now after multi-electron, yes, so is this. It's fine. So after multi-electron, what people thought that they will introduce spin orbit interaction, right? Now you introduce another term to the Hamiltonian. So first was your Hamiltonian was simple Hamiltonian, just p square by 2 mu minus z square by 4 pi epsilon 0 r for a single hydrogen atom. Next, what people thought ki not all the atoms are like single electron like hydrogen. So there can be multi-electron atoms. So for that they modify the potential. So VR term. So this term is modified now to introduce multi-electron things. So after modification, so VR is modified like this: E into ZR by 4 pi epsilon 0 R. So ZR is the effective charge. You don't need to remember all these formulas, just I'm just telling just to remember the story, okay? So now your VR is modified for single electron to multi-electron, and because of this modification, what happens? Now this L degeneracy is removed. So initially your energy was minus 13.6 pi n square. Now all the L levels were same energy in Bohr model, but now here all the L's are of different energy. Fine. Now next what people thought, okay, okay, this is not the end. So then people thought ki spin orbit coupling can be there, right? Electron spin can couple with the orbital angular momentum. So you can have spin orbit coupling Hamiltonian also, another extra term in the Hamiltonian. So this is proportional to H dot L, spin and orbit coupling term. Okay. Derivation you will learn in atomic course any. I'm just telling. So there are some spin orbit coupling term also. So this one H dot L you can write as J square minus what's this. Hi Kiran, can you just switch off your mic?
Yes, sir.
Okay, okay, fine. So this will be given by J square minus S square minus L square. So main thing of spin orbit coupling is that now your spin S and orbital angular momentum L are now coupled. So you no longer have these quantum numbers L like this. Okay. So up to this your quantum numbers were N, L, Ml, Ms and Mi for nuclear. You still didn't touch the nucleus. Okay. What you touch now? Orbital and spin L and S. Now they are coupled. So Ml or L, these are no longer a good quantum numbers, right? or ms or ml, these are no longer good. So due to this, what you have, n, l, and ml, ms you have coupled, right? So you have now j, mj, mi is remains same, the nucleus you didn't touch it, where j is given by s plus l. Okay, j can go from mod of l minus s to l plus s, and your energy, like Hamiltonian eigenvalues, are now given by E n l. Multi-electron E already become E n l. I mean energy depends on L. Now it depends on J also. E n l j in spin orbit coupling, right? So J can go from mod of L minus S to L plus S. Okay, so roughly you come here again. So you have S equals to 0, sorry, L equals to 0, this level, right? L equals to 0 level. If L equals to 0, nothing will happen. What is J? So for L equals to 0, J equals to half only, because electron has spin half, right? So J equals to mod of L plus minus half. I mean, J can go from L minus half to L plus half. If L equals to 0, J has only one value, that is half, right? So it will not split further. So in this case, your energy is E, N, L and J, right? So you have, it was 1 S and J is half. So in this case you write like this, 1 S half is your state. I mean the notation will be N, L and J. So N stands for N quantum number, S stands for L and half stands for J. So this is your first state. This is 1 S half. Its energy will remain same whether it is in Bohr model or next multi-electron or next spin orbit also. It will remain same because L is 0. Here also it will remain same and the state will become 2s half. But now when L equals to 1, if L equals to 1, J can have two values, right? 1 minus half and 1 plus half. So what are the two values? Half and 3 by 2, right? 1 minus half is half
Half and 3 by
and 3 by 2. So now L will break into two terms and the notation will given by 2p half and 2p 3 by 2.
2 3 by 2.
Hmm. Now similarly the upper one, n equals to 3 level, s equals to 0 will remain same. So it is 3s half, but 3p level it will break into 2. Now the degeneracy is lifted. So it will break 3p half and 3p 3 by 2.
3 by 2, 3p of
So now you break this. Now people thought ki okay, we have accounted the electron spin and orbital Hamiltonian. Further, what we can like accumulate in the Hamiltonian? Is there any further? So they thought yes, there can be further because they haven't touched the nucleus yet. So they thought ki nuclear spin. In this case, it has only one proton, that is spin half particle. So nuclear spin can also couple with the electron angular momentum. Like electron and nucleus, one is negative, one is positive charge, there can be some interaction. So that interaction, so they put another coupling term, that is nucleus spin and electron angular momentum interaction. So they thought we can add more here, that is, we can split the energy levels more. I'll just erase this portion once. Where's my eraser? Okay, let's erase this one a little bit. So this is your NLJ. Now further they assume ki electron can interact with nucleus also. That term also they define another Hamilton. So they define for that. Similarly, S dot L was spin and orbit, and now nucleus spin and orbit, right? It was electron spin and orbit, now nucleus spin and orbit. Nucleus spin is given by I. So this is I dot. Now you don't have L, right? You have already J, because L and S doesn't, like, they are not different. They are, you have already accumulated as a J equals to L plus S, right? So instead of L you have now J. J will stand for angular momentum, that is the total angular momentum, because in this approximation, spin orbit approximation, you already assume that spin and orbital are coupled, and that's why you define another new term, that is J, the total angular momentum. Now in the next approximation, nucleus spin and orbital, so the coupling term will given by I dot J. I stand for nucleus spin and J is the total angular momentum. And similarly you can define this like f square minus I square minus J square, where f is given by mod of J plus minus I. That means f can go from J minus I to J plus I. Okay, so this is another quantum number, another new quantum number you can say. This is f quantum number. So what will happen now, just again I am telling, don't remember, I'm just telling the story. Okay, derivation you will learn in atomic course. So what will happen now, so now in this case, suppose your nucleus spin you will be given. Okay, for every atom nucleus spin is, you will be given that, this is, you know already, that is nothing you have to derive. Okay, nucleus spin is fixed, so that you will be given. Suppose for hydrogen it is half. Suppose for the atoms you are given that I is equals to half. If nucleus spin is half, then what will happen to the first state, that is the first level? It was 1s half, right? That means J equals to half was here. In this case it was J equals to 1 by 2. Now what will happen? If I equals to half, J equals to half, F can go from what? F can go from half minus half to half plus half, right? So F has two value. One is 0, half minus half. Another one is half plus half, means 1. So now,
The 2
yeah, now 1 is half will be degenerate. Degeneracy will be lifted. Now here it will break into two levels. One will go to, one is the below one, it is F equals to 0. The upper one, F equals to 1. And here your energy will depend on E, N, L, J and F also. Similarly, 2s half levels, it will break into two. One is for f equals to 0 and one is for f equals to 1. And 2p half level, what will happen to 2p half? 2p half level will break into how many parts? L equals, look, j equals to half, I equals to half. It will also break into two parts. One is f equals to 0, f equals to 1.
1.
But 2p 3 by 2, this level will break into how many parts? So j equals to 3 by 2 and I equals to half. So it
0,
can,
1, 2.
so it will 3 by 2 minus 1, so it is how much? It will break into three parts, right? I think. Not three, I think it will go how much? J minus half is how much? So J plus I 2, right?
Mm, 1 by 2. 0, 1, 2. Is it, sir? 4 by 2, 2.
So this is 2, right? J plus half is 2 and J minus half is how much? 3 minus 1 is 1, right? Correct, right? So it has 2. J minus
Okay.
half is
Yes,
1.
yes, yes.
So f equals to 1 and f equals to 2. So
0
it will
minus 1.
also break into two parts, but the f values are different here. Not 0 and 1. One is f equals to 1, another is f equals to 2. Similarly, we can calculate for other levels. I'm not doing. So this is kind of all the, that is how you atomic physics, you break all the degeneracy and you get all the sublevels like this. And further you can break these f levels also. If you apply the magnetic field, some external magnetic field, if you can apply, then that magnetic field B can interact with F. Okay, then another Hamiltonian will come B dot F, that will lift this F degeneracy also, like MF value, like suppose F equals to 2, it will break. If F equals to 2, MF has how many value? MF can go from minus F to plus F, right?
Minus
So
2 to 2.
minus 2, minus 1, 0, 1, 2. Like this. Now all the MF has till now have same energy, right? Unless you apply any external magnetic field, all the MF will have same energy. But the moment you apply an external magnetic field B, what will happen? All this MF will now break. MF equals to minus 2 will come here. MF equals to minus 1, MF equals to 0 and MF equals to 1 and 2. So all will break. So this is the furthest breaking you can go. Okay. After that you don't have anything to break. So this is the complete atomic picture, like that is how you write the complete Hamiltonian. So you start from Bohr. So Bohr was the first person, so it was very simple. So Bohr Hamiltonian, you write just p square by 2 mu minus the potential, electrostatic potential term, that depends on 1 by r only, like 1 by 4 pi epsilon 0, 1 by r. It was the very simple. Then people thought ki okay, we can modify for multi electron. Then they defined it may not be 1 by r, So just simply write V of R. It can be any function of R. Then you come to spin orbit interaction. Then you write, like, you add another term h of spin orbit that lifts the degeneracy as I showed you here, like 2p half 2p, like the j term comes now. Then again they add another term, that is nuclear spin. There is a nuclear spin term
Okay,
and
so
orbit interaction. So that will give you the f values. And further they told ki if you want to lift the f, like you apply any external magnetic field, so you add like nuclear spin and external magnetic field B. So this is your complete Hamiltonian now for a atom. Okay, so that is how in any atom you got all the states. So your two level system can be this. It depends on which picture you are now. If you are only consider Bohr picture, then n equals to 1 and n equals, these are your simple two level system. So this can be your 0 or ground state, and this can be your excited state. So if you are dealing with, you are telling ki in your calculation we don't need to go further, multi-electron approximation is enough, then 1s will be your ground state, that is your 0. Suppose you are giving a light of energy this much separation, it also depends on light's energy separation. Then if your h cut omega is this much, then this can be your ground state and this can be your excited state. Or if your light energy is h cut omega prime is this much, then you have to consider these two is your ground and excited state. Then it will be excited state will become this one instead of 1s and 2p. Now you go to further spin orbit term, then this will be your ground state maybe. It depends on, again I am telling light energy. So 2s 1s half and 2p half. This can be, if it is h cut omega, this can be ground state, this can be excited state. Okay. Now you know the energy separation. Suppose you are dealing with calcium atom. Calcium 1s half and 2p half energy separation you will be given. I mean, from spectroscopy people have find out. There is a table or chart. So that's how you know that for calcium or any other atom, what is the separation between these two levels. Okay. So it depends on in which approximation you are. What will be the ground state? Even if you are dealing with two level atom, so what are the two levels? So this can be this or this. I mean, it depends on the approximation you are now. Understand? These also can be these two, like f equals to 0 and 1. These can be your two level. I mean, no problem. If you can apply the light energy of this much, h cut omega is this much small, then these two can be, one is ground, f equals to 0 is ground and f equals to 1 is your excited state. So in this case, you can write my excited state E like what will be 1 s half and in the bracket f equals to 0. So your excited state E means 1 s half f0 and ground state G means 1 s half, sorry it is f1 and f0 is your ground state. So these two yours, your one is ground and excited state, and you are giving light. These two are your ground and excited state because you are giving the incident light energy is h cut omega, which is the separation between these two levels. I mean, which is the same as the separation between these two levels energy. I think it's clear, right? So I'm just telling all this because just to get what is your ground state and excited state in two level approximation. So it depends everything on where are you now. I mean which approximation you need. It depends on the situation. Suppose you are not giving an external magnetic field, then this MF degeneracy will always be there. So you don't need to consider that MF0, MF1 is my any state because they are not existence unless you give any external magnetic field, or unless you consider the nuclear spin and orbital interaction, then you don't need even F values also. You can stop here till spin orbit here. You don't need to go further to there. Okay. I am telling all this because in initial lecture I think nothing is the initial quantum mechanics. So I think it is better to like these will be helpful later in the upcoming lectures. So next is the another concept you need to know like parity. So I hope everyone now understand what is my ground state and excited state, right? So I am again telling. So it depends on the situation. Where are you now? So I E and G can be anything. Okay, it depends on the incoming energy. So now you have so now there remains one question. Suppose you have an electron in suppose one is half state. Okay, you have an electron here. One is half state here. I am not going further to the nuclear level. So I mean for my problem, suppose up to this it is enough. So now 1 is half is my ground state. So one electron is here. Can this electron go to 2s half state or 2p half state? It is a question, right? Even if you can sign suppose h cut omega light, it may be possible that electron cannot go there. Like even if it can go, it cannot stay more in that level. It is because there is a parity of this case. That's why you need to know the parity things. Because all the transitions probabilities are not same. Like there will always be some probability that electron can go from s half to p half or s up to 3 by 2, but it may not be like probability can be 1% and 99% chance that it may not go. So all depends on the parity of the two states also. Like the transition probability depends on the parity. So what do we mean by parity? So if I write in the words, I will just write. So suppose this is my excited state. You have these two level atoms, one is G, one is E. So transition transition probability between these two levels depends on the parity of the two states. Okay, Whether this electron can transit to the excited state, it depends on the parity also. So what is the parity? What is the parity? So anyone knows the parity operator? Screen is not visible. Screen is visible, right?
For me, it's
Yes,
not
sir.
visible.
Screen is visible.
Okay.
Now it's visible, sir.
Okay, fine. So suppose you have a state psi and you have an operator. You have a state psi. Sorry, so you have a parity operator. Shit, what is it? Parity normally, what is happened? Pain is not. Okay, this is given by this pi cap operator. Okay. So what the operator does? So you have a wave function psi, and what parity does? Parity changes to psi prime. Okay. Now what is psi prime? So the definition is psi prime to minus of psi x cap psi. So this is the definition of parity operator. So the average of your position vector is negative of the average of your in old state position vector. So in your old quantum state, the position vector average was psi x cap psi, and the new state the average is negative of that. So the role of parity operator is this. And the new state, how you got? We apply the parity operator to the old state, you get the, I should better write, this is new, this is old. So this is n means new, and this is old. So parity operator change the old state to new state like this. Psi new equals to parity operator psi old. Now if you take the average of your position in the new state, it will be given by the negative of the average of your position in the old state. So that is the job of parity operator. Okay. So now we can write the psi n as like this. So this is the kit. So the bra vector will be given by psi n equals to, this will become first, right? Psi old and pi cap trigger, right? So psi n here you can write psi 0 pi cap trigger x cap psi n will be given by, this is pi cap and psi old, right? Just psi n you replace here, this one, these two you replace here, then you will get this. This is equals to minus psi 0 x cap psi 0, right? So from here you can check that pi dagger x cap pi equals to minus x cap. Also your states are normalized, right? So psi n equals to, this is given by psi pi dagger pi psi equals to psi equals to 1, right? So that implies parity operator pi dagger pi equals to unitary matrix or 1. Now you can check the x cap. Suppose the position operator, right, x cap, and you apply it on pi cap x. What will happen? I should write like this. And write this as minus x. This is the job of parity operator. Okay. This you can derive. This you try in your home. So use this one, equation number 2 and equation number 1. From these two you can derive that pi cap into x will given by minus x. So parity operator will just change x to minus x. Okay. That you can derive using 1 and 2. Similarly, you can just show, I don't have much time in this. If you take momentum also, right? So pi cap of p will be given by minus p. Fine. And also you can, later if we have time I will discuss again this one. But for now I'll just tell why you need to know the parity of the states in the two level system. So another thing is, suppose your system Hamiltonian is H, right? You can also show that pi cap bit commute with H. So all has same eigenstates. If your Hamiltonian H has eigenstate n, then pi will also have the same eigenstate n. You just read something about parity operator, then you will understand. Okay? Otherwise, I will discuss later also if you have doubt. So now the main thing was the transition probability, right? So this transition probability because between the two states, ground and excited state, that probability is proportional to the matrix element of n and n prime, or I should write this. Their notation is E and G. Okay. So gamma E and G. This is given by this. Suppose this is E, or suppose this is G. This is your E, then R cap. This is your R position vector and G. So this transition probability, what is the probability of transition from G to E? That will depends on this matrix element E, R and G. Okay. So if you break this now we have seen that pi square equals to 1, right? This pi dagger pi is equals to 1, and as pi is also unitary, so we can say pi square equals to 1 because pi is unitary. So pi dagger equals to pi inverse. Okay, so that's why you can say pi square equals to 1, the parity. So you can write it here E. You don't just remember the story, that will be enough, I think. So E is here, right? So here you can put the pi square term because pi square is 1, right? I mean unit matrix, so it doesn't matter. So here you put pi cap and pi cap, and next R is here. Okay, here also, wait a minute. Here also you put another pi cap into pi cap, and G is here. Okay, now suppose E state has parity. Suppose your excited state, this one has parity pi E, and ground state has parity is the question. Can you put pi rather than pi dagger pi? Yes, I can put because pi square is 1, that you can prove. Okay, so instead of 1 I am writing just pi square. So this is the properties of parity operator, that pi square is 1. That's only why I am using here. I mean I should write this comes first, Like first you have this property that pi square equals to 1. From there you can derive that pi dragger equals to pi inverse. Like this is the property of pi parity operator, that pi square is 1. So what I was telling, that excited state has parity pi e. And another property, if you study the parity operator, you will get pi has eigenvalue plus minus 1. Like these are the properties. Pi square equals to 1, and this implies pi dragger equals to pi inverse. Okay, and this also implies, from here you can show that it has eigenvalue plus minus 1. So parity can be plus 1 or minus 1. Okay, but suppose I don't know what is the parity, plus 1 or minus 1, for the ground state and excited state here. So I just write this as pi e and pi g. So pi e can be plus minus 1, pi g can be plus minus 1. But the exact value I don't know now yet. Okay, so I just put it as pi e and pi g, the parity of the two state, ground and excited. Okay, so that's why I can write that pi cap g, that I can write as pi g of g. Okay, and pi cap e, I can write pi e of e, because pi and pi g values I don't know yet, it can be plus 1 or minus 1. So I just write it as pi g and pi e. Okay, if I write it like this, what will happen? As it is real value, right? Plus minus 1. So this will be given by e into pi e. Okay, you can write it as dragger also, pi dragger, pi whatever. Okay, it doesn't matter because pi square is 1. So this pi e and e, this will give you what? 1 pi e and pi g will come out. Again, I am telling you can write this pi dragger pi also, doesn't matter. Okay, pi e pi g comes out. Then what you left with? Uh, E remains here. Then you have pi cap R, pi cap, and this is G. Okay, now these two you see, pi cap R. Pi cap R you have shown, right? Pi cap x equals to minus x. Okay, pi cap x equals to minus x, so pi cap R equals to minus R. So one minus sign will come. So what will happen here? Pi cap R will become minus R. Then again what you have, next we have r into pi cap. So this will become minus r. So pi cap r pi cap. This term will be minus r, and pi cap will act on the minus r again. If pi acts on minus r again, it will become plus r, right? Like it's operating parity twice. One is r become minus r, then minus r becomes r. It's like this. So what you will gain? You will get a negative sign only. Just a minute. Wait a minute. Doing something wrong here. Kappa is minus r. Wait a minute. Something I'm doing. Okay, let's do again this part. Something is wrong. Okay, pi cap r is minus r. Then this portion. Let's write this clearly. Pi square. So this one I should write clearly. Pi square and pi square. Okay. Yes, you are correct. I think I should write pi dragger pi. Yeah, someone was telling, so you are correct. I think I should write pi square pi. Then what will happen to it? So pi e equals to pi e into e, right? So this pi cap dragger is equals to e into pi e, and this one pi r cap is minus r. Now pi r cap into pi dragger. This will be given by minus r into pi dragger, right? So minus r into pi dragger, what will give? Like this one. Suppose here you put just approximately, you can write, sorry, this one you can write so it's like if you apply this minus r pi cap to the minus r, you will get back r, right? But I am applying here pi dragger, I mean pi inverse kind of thing. So you can just do the analogy like for quick checking. So if we apply pi to minus r, you will get r, right? Now if we apply the inverse of pi, so what will happen? The inverse of pi to the minus r, then you should, it will inverse the result, right? So r may become minus r. That I have to derive now. How to derive this one? Hmm, okay, pi into r is minus r, minus r to driver. Just wait a minute, I don't need to do all these things now. It's pi cap of minus r, So minus R of pi cap dragger is R, right? So we can use this one here. So from here we can write so E of pi cap dragger, right? The first term. This will be given as E of, so pi will, I can write just a minute. This is pi E pi G, these are scalars, so comes out. So you have E pi R cap pi dragger and G. Okay. Now you have pi E pi G E pi cap R is equals to minus R, right? So it will become minus R cap pi dragger G. Now minus R cap pi dragger will become R, right? So pi E pi G E R cap G. Is it okay? So the transition probability will depends on this pi E and pi G, the parity of the two state. Okay, that's what I am telling. So I think this is all you need as a starting of this two level atom. Now I'll do some simple math things there. I mean these are all formulas, nothing physics is there. It's minus 1 means. So you have what? Pi Eg equals to this kind of thing, right? So pi Eg into 1 minus pi E pi G equals to 0. So if this term becomes 0 kind of thing, then pi Eg can be anything. So that's what I'm telling. if this term is non-zero. Okay, yeah, it depends on, so pi g can be plus 1 minus 1, so 1 plus 1 or 1 minus 1, it depends on that. if if this term becomes 0, then pi g can be anything, right? But if this term becomes 0, then suppose if pi eg equals to 0, when you can say pi eg equals to 0, when you confirm that other term is non-zero, then pi eg has to be 0. So if the other term, I mean this term is non-zero, then that transition will not be possible, like pi eg is 0, that's what I'm telling. Okay, I'll do a simple math, I think, using the formulas you used in the class. Okay, I'm not explaining anything now. Suppose you are given a state now. These are nothing theory, just the problems related to your last things. Suppose this is your wave function psi theta comma phi is given by this, right? Cos theta by 2 0 plus e to the power I phi sin theta by 2 1, where is the range for theta and phi? Theta belongs to 0 to pi and phi belongs to 0 to 2 pi. I think. So this is your any normalized qubit state, right? This is the expression for any normalized qubit state. What's this? Screen is not visible. But everyone's screen is visible, right? Not visible. Okay, I'll share again, I think.
Now it's visible, sir.
Okay, fine. So this is your any normalized qubit state, right? So if I add any global phase, will the state change? Now suppose I add some global phase, just add some global phase. Suppose e to the power, what should I say? Some any other phase you can take. Suppose I add this, will that thing change the state of the set? Okay, suppose your state is given by, let's do it like this. Psi is root 3 by 2 0 plus e to the power I pi by 3 by 2 1. Okay, this is your state. So just find the theta and phi for this state. What will be the theta and phi for this state? So this is area is nothing is there. Cos theta by 2 equals to root 3 by 2, right? So theta is how much? Pi by 3, I think. Pi by 3. And phi equals to also pi by 3. And if can, so you can write this state like this, right? Some alpha 0 plus beta 1, where mod of alpha square plus mod of beta square equals to 1. And if you compare, you can say that mod of alpha equals to cos theta 2 and mod of beta equals to sine theta 2. So if you add any other phrase like phi plus something or something, so that doesn't change the thing, right? Because this modulus will remain same. That's what I am telling. Now you find the Bloch vector of this state. What will be the Bloch vector? So your state is given by this. Now you are asked to find the Bloch vector of this. Now in general, suppose your general state is given by psi theta phi equals to cos theta by 2 0 e to the power I sin phi sin theta by 2 1. Now what will be the Bloch vector of that? So in general case, suppose Bloch vector of R of psi, the general psi, okay, that is given by use sigma vector psi, okay, so that is given by psi sigma x psi. This is the Rx component, I mean 3D vector, right? So this is the first component. Second component psi sigma y psi and psi sigma z psi, okay, where sigma is the Pauli matrices, right, that you already studied. Sigma x, sigma y, sigma z. So you can verify like Rx, what do you expect? Rx sin theta cos phi, like this, right? And Ry sin theta sin phi. You will get the same thing. Suppose if you calculate Rx, just calculate psi sigma x psi, okay. Now psi you take the general state cos theta by 2 0 e to the power I sin e to the power I phi sin theta by 2 1, okay. Now just calculate this one. So what will be the Rx? So your psi is given by your psi is what? Psi theta phi is given by cos theta by 2 and e to the power I phi sin theta by 2, right? Sigma x you know. Sigma x is given by 0 1 1 0, right? Now you calculate. If you calculate, you can check this. Do I have already calculated this one? This was coming out cos theta by 2 to the power I phi sin theta by 2 plus to the power minus I by sin theta by 2 cos theta by 2. So this is coming out to be 2 cos theta by 2 sin theta by 2 cos phi equals to sin theta cos phi. Similarly, we can show the other ones. Ry is psi sigma y psi, that will given by sin theta sin phi, and Rz is equals to cos theta. Okay, so for a general psi state, your general position like Plot's vector r theta phi is given by this sin theta cos phi sin theta sin phi and cos theta, right? So this is your general Plot's vector. Now in this case the theta phi is you already calculated for the given state, like this root 3 by 2 0 e to the power I pi by 3 by 2 1. For this case your theta is given by theta equals to pi by 3 and phi equals to pi by 3 also. So for this state your Bloch vector pi by 3 will be given as so sin pi by 3 cos pi by 3 sin pi by 3 sin pi by 3 and cos pi by 3. So this is first term is root 3 by 4 3 by 4 and 1, right? So this is your Bloch vector for your state, and if you take the modulus of this, take the mod square, okay? So r of size mod square, then you have 3 by 16 plus 9 by 16 plus 1 by 4. This is 3 plus 9 plus 4, right, by 16 equals to 1. So as it is a pure state, so it has to be 1, right? So it should lie on the Bloch sphere, right, for pure state. So this is your theta and this is your x, y, z, is your phi. So it has to lie on the Bloch sphere, on the surface of the Bloch sphere, right? Because it is a pure state. And that's why it is 1 also. Pure state. Later you will see that for a mixed state, it can lie inside the Bloch sphere also. In that case, it may not be 1, it should be less than 1. So only for pure state, it will lie on the Bloch sphere, on the surface of the Bloch sphere. Fine. If you have any doubt, otherwise we can wind up for today. I think I don't have anything. So today I just give some introduction to two-state atom because it was initially quantum mechanics that we all many people know, right? So that's why I just give the two-level atom. They kind of try to give from where these two-level atoms are coming and what is the thing. If you feel it's more theory, you can write, or otherwise I will do more math. It depends like this. Yeah, joining late, no problem. I'm just asking, should we do more problems or it is okay, like some little with story kind of theory? Okay, then we'll meet on the next week then, if no question.
Thank you, sir.
Hello?